Thank you very much, Janice. So yeah, today's lecture is about generative AI and how it's related to robotics. So I will do, let's say, simple or basic introduction about generative AI, and I will try to cover some of the important and most basic concepts for both diffusion, flow matching, and imitation learning. And the second lecture later will be more focused about the VLA, that will go through more advanced and foundation model topics. So I will go for simple introduction. I will try to focus more about really understanding what is a generative method, because we talk a lot about them, but it's important to really have a clear idea of what exactly this is. I will talk about diffusion, but mostly about flow matching, which is basically a different version of diffusion, and some introduction about imitation learning. Some of you may know already this topic well, but this lecture is mostly about introduction for people who don't know, who have never heard about a generative model, or how this is applied to imitation learning. And I will go, if we have time, for some implementation details later. So again, this topic will cover different kind of topics. So it's easier for me or for us if you have any question, please ask them directly, because it will be much easier if you don't wait until the end if you have any question or anything is not clear. So as Dionys suggested, explained very well. So I started my PhD in 2013. That was about 13 years ago now. And I've been lucky to see the evolution of robotics over several years. So as Dionys mentioned, when I was in PhD, I was working with small humanoid robots that were doing football in a Robocop competition. At that time, the robotic was, the behavior was simple. Most of the behavior of the robot were mostly manually engineered. There was mostly scripted behavior. There was a lot of state machine. The machine learning that were applied was not deep learning. It was simple regression, non-linear parametric regression. For vision, there was a classic old OpenCV, like a kernel, filters, all these kind of things, no neural network. And so that was, let's say, the classic robotics with lots of engineered and predefined motions. There was a time after 2013, after the DRC, the Dark Robotics Challenge, where the community used more and more, let's say, optimal approach for planning and control. So basically, we have the problem of planification and control, and they are cast as the optimization problem solved with mathematical tools. And in this, so typically for planning and control, robotic control, I apply that for multi-contact, a bit for this big humanoid robot in NASA, and also for teleoperation things, to solve some whole body problem control and multi-contact. And after that, I did work for teleoperation, which naturally led me to imitation learning. So you have seen that the rise of AI now is really crazy. Everything goes so fast. I think that, honestly, robotics is now fully coupled with the progress of AI, and robotics is nearly a downstream application of AI. I think it's hard not to at least know a bit about the generative method AI if you want to do robotics now. So from this very model-based classic method that use mathematical understanding, at a time when we could understand what the robot was actually doing, going through deep learning, imitation learning, generative method to apply to also humanoid, but different kind of manipulation tasks, from locomotion to more manipulation tasks. I'm going to describe a bit. So again, for generative AI, they are now everywhere, and we know that have been applied in many very trendy topics recently. We heard about ChatGPT and the LLMs that where we discussed that yesterday. Most of them generate text, tokens, they can do chatbot, they can do code, etc. There is also a whole family of models that generate medium, let's say, images, music, speech, videos. You heard about Stable Diffusion, there is Midjourney, there is Sora for videos, there is a lot of different kind of models that generate different kind of output. And this kind of generative model are also applied to robotics. So here I mentioned VLA that will going to be presented later, but there was also smaller models, imitation learning, which can handle a single task, also relying on this technology. So today, actually, I'm going to focus on the two later part of this family. I will not talk at all about the ChatGPT or LLM style, because the kind of generative models they're using, even though they're solving the same kind of problem, are actually very different. This one, because ChatGPT and LLMs output a discrete set of tokens, while all the diffusion and flow matching family of generation output continuous data. And even though the problems they're solving is the same, the method they are applying is very different. So we're going to focus today on these two later parts of the family. And just to give you a bit of motivation for this lecture, some of the work I did in the past 2 years here actually at Inria. Also, so using this imitation learning with generative method, explicitly flow matching for robotics. So on this Talos robot, we apply that for solving manipulation tasks with multi-contact. So you can see that the robot sometimes puts his hand on the table so that he is more stable, he can control the box which is far away and apply more forces. Here the robot can close the door of the dishwasher by putting his hand on the top of the dishwasher and lowering his body lower. And other work with in the kitchen manipulating object in different long horizon sequence. So all of this, the lower part of the architecture, the things that control the body, was classic model-based method, but the higher part of the behavior was trained with imitation learning using a flow matching and generative model. So I will try to give you the understanding of what is a generative model. Because we heard a lot about it, we heard about generative model, generative AI, everything, but exactly what is the problem that is being solved is we need to understand exactly what is the problem here. So for those who have studied a bit machine learning and AI, you know that the most basic things we can do with AI is, okay, it's called supervised learning by the learning people, it's called regression by the old guy for machine learning, but it's basically the same things. We have a data set of pairs of question and answers. We have a big data set of these, and we are trying to learn a function, a nonlinear function that goes from the question to the answer. So it's a very basic problem, either through classic linear regression or nonlinear neural network. But we are trying to build a deterministic function that goes from the question to the answers. So that's the basic things of deep learning and AI, but in generative model is not this. It's really important to understand that generative problem is a different kind of problem than this simple question to answer deterministic question. What we are really trying to do is about probability. Let's say we have some data that are taken from a probability distribution. For example, here in the 2D plane, a 2D distribution with x and y that looks like they are taken from a uniform distribution that have the shape of a square. And all these blue dots here are the dataset we have collected. The whole problem of generative AI is to model these distributions, to understand that this is actually a kind of square, and most important, to sample new example from the distribution. The whole point of generative model is we have a data of some distribution, and we're trying to generate new sample from this distribution. Typically, you have images of cats. You have a lot of images of cats, and you want to generate new images of cats that are different from the one to the dataset, but still looks like cat. And fundamentally, this is a stochastic process, which means every time you're going to generate new samples, every time you're going to call your generative process, it will be a new answer. It will be a new point. Every time it will be different. It will be random, but the data will be inside the distribution of your data. If the model has trained well, it will be here it will be a point that inside the square, or if you are generating an image of cat, it will be a cat in the image, even though the cat is never in the entire dataset you have trained for. So a very important properties we need to understand is multimodality. So I'm not talking, so mostly complex distribution are about multimodal data. So by multimodal, I don't mean, so it's a question of vocabulary, I don't mean several modalities. So I don't mean different image, text, sound, or touch. I think of different modes in the probability distribution. Typically, a Gaussian is a unimodal distribution, and we can have bimodal, multimodal distribution. The point that I wanted to make is many of the interesting complex distributions we are talking to are multimodal in a sense that the support is non-convex. Typically, if you have a point in this part of the distribution and a point in this part of the distribution, you cannot take the average of them. You cannot take the average them and end up inside the distribution. So the distribution is not convex because you have some peaks which represent different kind of modes. So what I want to say is generative model is much more interesting to apply with multimodal distribution, and this is important when we will be dealing with imitation learning. We're going to go to that later. So a first example to try to understand better what is to understand what is a generative model is go through the classic method of Gaussian mixture model. So this is not exactly a generative model, but it can solve the problem of generative AI, and it's a way to understand what is the problem exactly. So typically you have a data set made of lots of different points, which is, you can see it's multimodal, it's non-convex. And the idea of the method is to fit a bunch of Gaussian to try to model and represent this distribution. Typically, we can take 4 Gaussian to cover the data set we have in 2D. And to learn the parameter of this Gaussian, so the parameter of the variance and the position of the Gaussian, as well as the relative distribution between each of them. And when we have that, we can sample new point in this distribution by just select which Gaussian we want to sample, for example, this one. And when we know this Gaussian, we can sample this Gaussian to generate new points of the distribution. So again, this is an example of generative model with classic machine learning tools, which has the benefits of being explainable, interpretable, because everything is known. We can compute everything, any likelihood we want, because it's a bunch of Gaussian. We know very well how to handle this. This is easy and fast to train, but the downside is it actually does not work very well for high-dimensional distribution. When we see a complex distribution, you can see that the fitting, if we want something very accurate, we need a lot of Gaussians, and basically do not scale well to large database and high-dimensional space. So this is a classic approach, but of course, modern generative AI has more complex methods. Few of the methods I could talk about, just to mention, I'm not going to explain them in detail, but just to mention that they exist before diffusion and before flow matching times, where, for example, the GAN for generative adversarial network. So you may have heard about it. It's basically made of 2 modules. One generator that will try to create the best fake images or best new samples, and a discriminator that will try to determine if the data is come from the real dataset or from the generators. And each of them will be trained by competing against each other until the discriminator becomes very good at telling which one is the real data, which one is the fake data, and the generator tries to fool the discriminator as best as possible. The problem with that is it's rather unstable to train. So because there are 2 components that are competing against each other, sometimes training are difficult and can be unstable. The same problem of instability happens with another method called the VAE, variational autoencoder, that has different kind of ideas. Not going into the details, but has the same things. Also other kind of method, energy-based model and others. So the good points with the flow matching and diffusion methods are, first, they scale very well to high-dimensional data, and you've seen that they can generate images, videos, robot action. Their strong point is they are good at high-dimensional data, and they are good at capturing complex, multimodal distribution, as I was talking about. And most importantly, they are more stable to train. And I think personally one of the biggest advantages of this method is they are very, let's say they are kind of flexible, meaning that even though the method is not too difficult, they are easy to add new ideas, easy to derive different flavor of the algorithm. We can tweak them to change them, to add them many different kind of properties. It's easy as a research to work with them because we can try many different kind of ideas with them. And because they are very flexible, I think this is the reason why that they become very popular. On the downside, they have slower inference time. So they are to do the generation, to do the inference time, it takes longer than the GAN or VAE, even though, because they are flexible, as I said, there is a way to negotiate, there is a way to improve them, and we can make them faster if we want. So try to go thoroughly into this idea of flow matching and diffusion. I will try to talk about, just quickly, for the people who have heard about it, of a method, a model that we called denoising autoencoder, just because it gives the intuition of what's happening during diffusion. So this is not really used for diffusion, but you can see that this is an interesting concept. The idea was we have clean data, for example, images taken from numbers. So this is the clean data, and we will add a bit of noise to them. So we will corrupt the data with adding a bit of noise, and we will train a model. So this is not generative AI, it's purely supervised learning, and we will train the model to go from this noisy data to go back to the no noise data. So it's basically a model that removes the noise. And what it's doing actually is we imagine we have the manifold of the data, so the thin in the high dimensional space. the thin non-linear manifold on which the data lie. When we add noise to this data, we are going out of the manifold of data. And what we learn by doing the denoising autoencoder is what we learn to project back into the manifold of data. So we are trying to learn a kind of projector that go from any area around the manifold to the manifold of data, which basically create a kind of vector field that project back data to the manifold. Again, this is trained with supervised learning in a one-step manner. For example, we have a point here, and we learn directly that a point here belongs probably here. So this works not bad, okay, around the manifold, but do not work very well when the image is very noisy or very far away from the manifold. It works to remove noise around data that's not too much corrupted. The idea of diffusion is very similar to this, but instead of doing a one-step correction, it does multiple step correction to remove the noise step by step. So to give you the core intuition about diffusion is the following. So this is a classic way that things are explained. We have a clean data, we have an image of cat, and we will add a bit of noise, step by step, until we corrupt the data, until we destroy all the information into the data to reach a pure noise. And when we are doing that, when we are corrupting the data step by step, we're actually going from a complex distribution and to removing the information until we're merging to a fully noised, simple distribution. And then the whole point of diffusion is to learn a model that will remove that noise step by step. For example, we will learn to have this input image as a partially noised image, and we'll learn a model that will go back to this image with less noise by learning the noise we have added to the model. So when we are here and we add some noise, we learn a model that will take these images partially corrupted. We remember this is a very important point that we're at the step number k of the noising process, and we will learn to learn the noise we have added so that we can remove it later. So that's the basic idea of diffusion. I'm not going to go too much into the details about diffusion because I'm going to talk about flow matching today. The thing is, diffusion and flow matching are very, very similar methods. They are basically the two sides of the same coins, but they see the problem in a different way. So the core intuition you've seen with the diffusion is about adding noise and removing noise, and flow matching do basically the same kind of problem, but see the problem in a different perspective, which I'm going to try to explain right now. So again, the problem is we have a distribution, which is probably too complex, and we want to sample new data from it. But the distribution is too complicated. It's very high dimensional, and we cannot directly sample from it. It's too complicated. So the idea here is we will focus on something more simple. Typically, we know that we can sample easily from simple distribution, like a Gaussian or a uniform distribution. So the whole idea of flow matching is we know how to sample from simple source distribution. We want to generate samples from target complex distribution. So let's just create a transformation that will transform simple distribution into complex distribution. As simple as this. So to generate new samples, we just sample the distribution we know, something like a Gaussian or a uniform distribution. Then we we generate some samples, this one, this one, and this one. We use our nonlinear complex transformation to go from source distribution to target distribution. And then we have finally points that are within the target distribution. So this is the basic idea of the flow idea, with the difference is that instead of computing a single transformation in a one step, instead of trying to have a function that takes directly one simple from source and directly transform it to target, we learn a continuous step-by-step transformation. Again, we learn a continuous transformation which takes the form of a vector field that goes from source distribution to a target distribution, which looks like this at the end. So typically, during the tutorial, you will practice this kind of exercise first. At first, you can see we have a Gaussian distribution, which is purely noise, and we learn a continuous transformation to morph it into our target distribution, which is actually a role, as you can see here. And of course, the difficult task is how we can build, how we can define, and how we can learn this vector field that will do a continuous transformation between something simple to something very complicated. And for this, there has been different kind of methods. So old one, let's say, is called the continuous normalizing flow, which was used before 2021. And the new one, flow matching, which I'm going to explain a bit more now. So again, flow matching is related to a mathematical theory called optimal transport theory. And it's good to have, so I'm not going to the details, just to give you the rough idea of this theory. This is a mathematical theory, very theoretical, that were raised in the 19th century. And the problem is the following. We have a stack of sand, which actually represent, can be seen as a distribution with some mass. And we have two stacks of sand, a blue one and a source one and a target one. And the question is how we can move the sand from one distribution to another by moving the least sand as possible. So how we can transform a pile of sand in one shape to another shape by having a kind of mass conservation, which is equivalent to transforming a distribution to another distribution by moving as less sand as possible. And this has actually many applications in theoretical math, and both it can be used to compare two probability distributions and to find the best coupling between two distributions. So I'm not going to go into some details, but just to give you some facts that are important to keep in mind. First, this transformation is well understood for discrete problem, but it is hard in continuous settings. Second, there is an infinite way to transform one distribution into another. You can think that when we have a source distribution on the left and a target distribution on the right, the way we can map some points on the left to some point on the right, there are many ways we can do such couplings together. And in the general settings, flow matching compute one of these coupling, but it's not optimal. So there is no guarantee that the flow matching solution will be optimal. But most of the time, I would say it's not that bad. It's not too far away from the optimal one, but just keep in mind that the flow matching is not theoretically optimal. And second, other properties that, as I said, flow matching create a vector field. And because of this, the continuous transformation between one distribution into another make the mapping such that there is non-crossing path. Typically, in such path, when there is a crossing between distribution, is not possible with flow matching, and we had to have this bending in the coupling between two distributions. So to go back again to explain more the training, let's consider we have samples which are taken from a high-dimensional space, and we have this transport ratio, which is between 0 and 1, that represents how much we are progressing during the transformation. So in the literature, this transport ratio is often noted times, which I think is a terrible thing, because we are dealing with robotics, we are dealing with time-based problems, so it's not about time, we'll call it transport ratio here. And the whole point, again, is to build a model that will take as input the samples we are trying to transform. We are going to have the transport ratio, which is how much we are progressing between the source distribution and the target distribution, and will output our vector field. So again, the transport ratio, when it's equal to 0, it means we are at the source. When it's equal to 1, which means we are arrived at the target distribution, and anything between 0 and 1 is in between the transformation. So the training recipe for flow matching is the following. We will randomly sample one point in the source distribution. We will randomly sample one element in the target distribution. So when I say source distribution, we can easily sample them because it's known. We can easily sample a Gaussian distribution, let's say. When I say we sample a point in the target distribution, which means we have a data set of points, and we just choose one of them. And when we have these 2 points, we will create a straight line between the two by using this very simple interpolation, and we select one point in the middle. So we select one transport ratio between 0 and 1. We take the straight line between the 2 points, and we select this middle point. And when we learn the model, we make this call to the model. We have the sample here in the middle, which is being transformed. We have the transport ratio between 0 and 1, which is where we are during the transformation, and we will learn the vector field, which is a vector that goes from 0 to 1 here. You can imagine by using this tuning loss, this point, and the vector field here. The whole idea is, imagine we sample a transport ratio equal to 0, which means we are here. which means that when we are at this point, we are trying to fit at this point the one step vector that transforms x0 to x1 directly. And we do that all along the line by randomly sampling a point here. So I will try to give you a bit more intuitive understanding of what is happening. So again, we have a source distribution, which is a uniform distribution on the left, and we have, let's say, a bimodal distribution on the right. And we try to sample points randomly on the left and on the right. So when we do that, we create this kind of lines, this kind of coupling lines between the distribution. Again, what we are trying to learn is the 2D things. Remember that here the input of the model is a sample x and the transport ratio tau. So if our target distribution is of dimension 1, this is a scalar of dimension 1. So the things that we are trying to learn is a vector field of dimension 2 here which we can display here. So if we do that straight line many times, we end up with this kind of figure. And if you think about it, if you take a little area around the flow, what happens during training is we're going to aggregate many many vector fields. Typically, if we take the lines that go from here to here, at this point, we're going to fit as a regression reference in the loss function this vector. If we take the points that go from here to here, we end up with this kind of vector. And what happens when we train a neural network over time, over batches and over epochs? Basically, what we are doing is average over all the target reference we are given to the model. So at the end, we will learn one vector that is the average of all the ones that are individually trained into the network. Which means if a point which is here, on average, the vector will have that direction toward this distribution, and if we take a point here on average, because there are much more lines that go from here that cross here, will go in this direction. So just a way to explain that over time, the flow will be trained by sampling this line randomly, doing this linear interpolation, and over time, the flow will be learned to have this smooth structure. Again, this is the basic recipe for flow matching, and there are others way to do that. I'm not going too much into the details, but just to quickly, here we took random points on the source distribution, random points the target distribution, and just with a straight line we apply this and we end up with this kind of path. There is a way to improve flow matching by using insight from optimal transport theory, by having a better coupling between the two. For example, this is a small pre-processing step that is applied when we create the batch. We create some mini batch, we apply some computation of optimal transport coupling before the loss function, and we can improve the pairing between the samples by having more straighter lines. So this is not mandatory. It's a kind of optimization that if we want to improve the optimality of the flow that is learned by flow matching, we can apply this kind of technique, and we end up with faster inference. But again, this is not mandatory, and during the tutorials we will use the classic approach. And for inference, when we have the flow, it's easy. We just have to integrate the flow to start from the source distribution and follow the vector field until we follow the path to the target distribution. So one way to do that is through a simple Euler integration, which works very well. Typically, we sample a point in the source distribution. We sample a point here or here or here, and for the transport ratios that go from 0 to 1, we will follow the vector field until we reach the target distribution. So usually, with flow matching, we can discretize this integration of the flow with 10 to 20 steps, it's enough, while for diffusion it requires around 100 of steps to work well. And you see this example of morphing between different distributions. You can experiment with that this afternoon during the tutorial. Just to talk quickly about flow matching and diffusion, both of them, as I said, are the two sides of the same coins. And there is a framework called stochastic interpolant that combine both of them together. Basically, what we can say is flow matching is the deterministic version and diffusion is the stochastic version. Typically, when we have the flow that go from the source distribution to the target, when we do flow matching, we are following a path, deterministic path around the flow. But when we are doing diffusion, we do the same things, but the path we are following is stochastic, and it's basically a stochastic differential equation. The difference is that diffusion, because of this stochastic behavior, tends actually to work a bit better, to have better sample quality for very complex, very highly non-linear distribution. Mostly because flow matching has some issue concerning the topology we can discuss later. But the downside of diffusion, he has slower inference. On the other side, flow matching, because he has paths that generally are straighter in the flow, can be integrated with less steps and can be generated faster. Also, another advantage of flow matching is that we can use as source distribution any kind of distribution. It could be a Gaussian, but it could be uniform, or it could be something completely different, very complex. While diffusion has to be Gaussian according to the theory. So for robotics, most of the time we like things that are deterministic and we want to have something that have inference fast. So flow matching is sometimes preferred, and we have shown in some of our work that flow matching is actually perform a bit better than diffusion, but again, both of them are very similar. And some works use diffusion, some works for flow matching. Depending on all the flavor and the implementation, they could be somehow similar. Another point I really wanted to explain is that there is a big difference between unconditional and conditional distribution. So the distribution we are talking about here are unconditional, which means we just have a source to target distribution that do not have any other condition. When we do robotics, we often want to consider not just the probability distribution, but the probability distribution conditioned by some element. For example, we have image generators that can generate many kinds of images, but we want to generate specifically images of cat. We want to have the probability distribution of a real image, given that the image is a cat. So this is a way to have conditional probability distribution. And in the case of robotics, for imitation learning, we will have our condition, which is the current observation of the robot. Again, there is a different way to do conditional distribution with flow matching and diffusion. One is about inference guidance, when we do not train, which is only applied at inference and not require specific setup during training. One of them is in-painting. For example, you take an image, you add some black area in the image, and the diffusion model is able to fill the blank by generating noise only within this part and to fill the gap between the images. Another approach to do this conditional distribution is applied during training, when we learn a model that just simply has an additional input, which is a condition. And this is the method we are going to apply now. This model conditioning tends to work a bit more accurate in a robotic task, but again, the two could be applied. Typically, we will have a model that takes as input the samples, the condition, the transport ratio, and also a condition as an additional input, and we will rely on the interpolation of the neural network to handle this conditioning of the vector field. So now I'm going to describe a bit more imitation learning. So if you have any question about flow matching or generative method, it's the right time to ask any question, because we will, after that, assume that you understand this. We can talk about how they are used for imitation learning. So do you have any question concerning flow matching? If not, we can go directly to imitation learning. So imitation learning is an old topic in robotics that are more than 20 years. And the more specific flavor we are using is behavior cloning, where the idea is we want to solve a task by reproducing the human action. So again, the recipe is very simple. we have a task we want to solve, and we're going to have the human to show the robot how to solve the task. The most simple way is to do that through teleoperation. We have a human that will take full control of the robot. They're going to solve a task, and we're going to record in the dataset what the human is doing. Then, from this dataset, we're going to learn with flow matching or imitation learning a model that will mimic the human action. So given the same input, the same state, the model will learn what the human would have done in this situation, such that we can build reactive policies that go from observation, maybe proprioception of the robot, to action. So again, we are using generative AI because we will replace the human teleoperate the robot, solve the task, and we will replace the human by the policy by having the policy behaving like the human would have done in the similar case from the data. The main advantage of this method is we don't need to have any simulation, we don't need to have a reward function, we don't need to describe the task in a formal way to try to solve it. We just have the human to show how to solve the task, and we can use purely real robot data without simulation gap. So as I was saying, the imitation learning is an old topic in robotics, but it has started to work very well recently thanks to generative AI. I selected the 3 works that I think I like and I think they are important, but there are many others. And each of them have improved the state of the art of imitation learning by using generative method. One of them was based on energy-based model, a previous version of diffusion and flow matching. But one of the most important works that really shows that this method could work very well was this diffusion policy paper in 2023. Again, using a diffusion method, and new work, especially VLA 2024, using flow matching, that the next lecture is going to go into more details. Just to give you my current understanding and current vision about flow matching, about the current state and current context of imitation learning before going to the more technical details. First, imitation learning right now is mostly used for manipulation tasks. So there is a kind of duality in robotics that locomotion is solved with reinforcement learning and manipulation is solved with imitation learning. Why? Because reinforcement learning requires simulation, require many evaluation of the policy, which is sample inefficient, and we have all simulators that can handle locomotion very well. This is easy, but it's harder to simulate contact, harder to simulate manipulation. So because of this, locomotion is usually solved with reinforcement learning, and manipulation is solved with imitation learning. And something I would like to say is that globally, imitation learning works very well. So as I said, it has been a few years now that generative AI is applied to imitation learning, and honestly, it works very well. If you have any kind of task, any manipulation task that the robot can do, if you can teleoperate a task, then you can create a policy that solves the task if you have enough data. So if you are patient enough, if you have enough resources to collect enough data to cover all the variability of a task, any manipulation tasks you can teleoperate, you can make it autonomous with imitation learning. This is a very strong method that works very well, and that's why people start to think that actually we could build a robot, a generalist robot that can able to solve any task. So, of course, we are not there yet, and there is still many issues, but because this method starts really to work well on simple tasks, people start to dream, and companies many startups are being created trying to scale this kind of method, scale this method up, gather more data, gather more compute, and try to build a policy able to do basically anything. So the point which is important is we're trying to build a goal condition policy, which means at some point we want a model that will solve not just only one single task, but many kind of tasks, which require that the human will have to describe to this model what he wants to do, a goal. A goal could be provided as a language, as a prompt, as in the VLA, that we will be explained in the next lecture, but could be an image, could be a state, could be other things. But of course, it's not that simple. And typically, when we want to solve a task, we have to address some kind of variability. Every time we solve a task, it's never always the same, exactly the same task, which require a large quantity of data, because sometimes the task will be a bit different, an object will be at a different position, the target of the position when we want to place the object will be a bit different every time. This is the variability about the task, but there is variability about the environment. Maybe the lighting will be a bit different, maybe the color of the object, the appearance of the object will be a bit different. So to handle all this variability, there is no other solution than creating a large quantity of data. And usually, the bottleneck of such method is the availability of data to train this model. So there has been a lot of ideas of how we can scale this data, because collecting teleoperation data for every single task that exists requires a huge amount of resources, which usually is very difficult to do. So the last 2 years of research was how to use other kind of data to train this model to be able to scale up. Like we were training with LLMs that were using internet scale of data, huge amount of data. The whole idea in robotics right now is to try to find other source of data to train these models. Some ideas are using some cross-embodiment data, so not only data that come from the robot you want to do, but other kind of robot, maybe different humanoid robots that will collect data for bimanual robot or the opposite. And for example, last year in Coral, many people were trying to fit human data. Typically, we have a human that will have some motion capture that will collect a task which is less costly to collect than teleoperation, and many research are trying to use data that are not as close to the robot, but a way to either pre-train or to adapt the data to fill this gap of non-obtained data. And also, one of the goals of this line of research is to use internet scale of data, for example, YouTube video of everything, to fill the gap of this data. But again, this is very difficult. There is many research problems about that, especially for long horizon tasks. So tasks that require many steps, for example, cooking a recipe that requires to do this step, this step, this step, and these steps, which has a form of combinatorial explosion. It's hard to record data for every recipe you can think of. You can collect data with simple action, but not everything, all the sequence. So long horizon tasks are still difficult. And one of the interesting research directions that I'm not going to go in details, but basically is to apply some form of inference time computation. You know that for LLMs, the thing that makes them better is chain of thought. By using reasoning, by using some inference time compute, they were able to perform better. And one of the research lines that are ongoing right now in robotics is doing the same kind of things, having some more reasoning, some kind of planning, and maybe you have heard about world models recently. Basically, it's a way to improve the data efficiency, improve the generalization of this model through more compute during inference time. So that's just the big landscape of imitation learning right now, but I will not go too much into the details and go about the technical details and how they work. So to come back to the different kind of policies, as I said, there is different kind of policies that could be done, either through solving a single task or by solving different tasks. Solving a single task, we build a model that takes as input, let's say, images, robot probe images, which is what the robot can see, either through different kind of cameras or even point clouds, and the robot probe reception, which is the motors and the position of a limb of the robot, and this kind of models output robot action. Another kind of models doing the same, but as I said, they are goal conditioned, which means they have additional extra input, which gives them the goal we want to solve. In the case, this policy, these models can solve different kind of tasks, which can be either as the images or as the goal prompt with VLM. And try to make them, to explain you why generative model really improved the performance of imitation learning. There is basically two or three reasons. One of them is this model do not output a single action, but a sequence of action. So let me explain you that. In the previous model, the policy are like state, goal, and they output the single action. So at every time step, we are calling the policy again, and we derive every time one action, and we derive the policy like this. The kind of imitation learning we are using right now, instead of outputting a single action, we are outputting a sequence of future actions. And we are using We are using imitation, we are using generative model for this because they can handle well high dimensional data. For example, we go from a pure noise trajectory and we denoise them, or we use flow matching to generate a full trajectory of future action. And for example, during inference, we apply a kind of MPC style approach, which is we generate trajectories, we play these trajectories for a time. During that time, because we're in real time, we are generating another trajectories in the background, and when one is ready, sometimes we are switching from current trajectory to a new trajectory. The point I want to say is actually we are replanning all the time a new trajectory of action. And why it works is because it improves the time coherence. So when we are playing trajectories, we have less noise than as we are changing our mind every time. And it's basically an old idea in control. So when we do control, when we do classical control, there is this idea of feed forward versus feedback. So if we have a purely feedback, a purely reactive policy, we go directly from sensors state to action. And every time step we do this from state to action. This is a purely reactive policy. On the other hand, we could have, let's say, feed forward. Feed forward means we are planning what we want to do, and then we close our eyes. We don't care anymore about the external world, and we keep believing in ourselves, let's say, and we keep applying the action we have planned. Of course, we need to find a balance between the two, between reactive and between feed forward, but very often, when we do classic robotics, a bit of feed forward helps a lot in stabilizing a control. First, because feed forward is less sensitive to noise in the sensors. If you have a purely reactive policy and you have noise in the sensors, you will have noise in the output, which is transmitted directly. Also, every time you have delay in a control system, a delay between sensors and action makes a reactive policy brittle and very sensitive. So having a kind of trade-off between feedback and feed-forward is usually a very good thing in control, and this is one of the reasons that these generative methods are doing better. And the second reason that why generative method is really improving the performance is, as I said, remember before, about multimodality. Multimodality because many tasks, many complex tasks can be solved in different ways. For example, for a humanoid robot that will do multi-contact things, there are many options where to put contacts, many possible ways to put different kind of contacts. And when we are using teleoperation to record this kind of data, humans most often never do the same action twice. Humans are very multimodal behavior, especially when we are recording action. Typically, if you have ever do some machine learning in teleoperation, humans do some idle pause, idle time. When I teleoperate, sometimes I pause, I'm going to scratch myself and start again. All this little idle time, idle pause when we are doing teleoperation, create a kind of multimodal distribution in the action. And when we don't take into account this multimodal distribution, it tends to work much less, not as good as with machine learning. Another classic example is that a task can be solved in different ways. Typically, imagine you are driving a car and you have an obstacle, and you can either turn left or turn right. We don't care if you turn left or turn right. In any case, you're going to avoid the obstacles. But you have to choose between left and right. And if you don't choose, if you average the two solutions, if you have, let's say, 50% of the trajectories that go left, 50% trajectories that go right, and you use a classic method with supervised learning, what you're going to do is going to average the result. And when you average left and right, you actually go straight, which is really not the thing you should do. Because again, the distribution is multimodal and is not convex. So having a model that can, from the data that are complex, extract and really capture the multimodality of data is very important to solve complex tasks. And that's why these generative methods are really working better. And again, when we do imitation learning, the most important thing is data, of course. And it turns out that the performance of imitation learning is very highly dependent on the quality and the quantity of data. So first, when you want to solve a task, of course, you need to show the robot how to do it. And you need to show it how to do it well, which means that every mistake your operator will do when you show the robot how to solve the task, you should remove them from the dataset. You should remove any mistake from the dataset, because if you don't do that, the robot will learn to do the mistake by itself. Fundamentally, the model don't understand what it's doing. It's just reproducing, mimicking stupidly the action of the expert. So the quality of the data you take as input are very important for the end performance of the policy. Another thing is, again, the variability of the task. If you want, when you teleoperate the robot, when you create your dataset of demonstration, to cover as much variability as possible, you want to have variability in your object, that variability in your environment. The more state space you are covering when creating the dataset, the more robust will be the policy. Another thing which I found when I did this experiment of imitation learning, something that turns out to be very important is to include a recovery action. So let me explain you this. Imagine you have a task that go from some initial state, which is a distribution. So there are many kinds of initial state, and you want to reach a goal state. And usually, what you will do, you will ask your expert to solve the task. It will show how to. It will control the robot, and it will show you how to drive the task from the start state to the goal state, and it will show you the nominal action to be done. Turns out that this is not enough to have a robust policy, because most of the times, every time, your model will have some errors. And as time goes, when you do the inference and apply your imitation learning policy, there will always be a mistake, and you will end up, by following this nominal path, deviate a little bit and then a little bit more from the nominal path and end up in a different state. And when you are here out of distribution, your robot don't know what to do, because he has never seen in the dataset what to do in these cases. And most of the time, this is where the robustness failed and the policy don't work. That's why most of the time when you do your dataset, it's important to include the recovery action. For example, you know that along the nominal path, there is area of state space you should know how to recover from. So you do a mistake, you end up in this case, and you should know that when you are here, you need to do a special action, a special recovery action, to go back to the nominal path. And actually, this is actually very hard to do, because when you do the teleoperation, you have to keep in mind that, I need to reset the environment to this state, and this state, to show the robot how to recover from that. Because if you're just showing what to do when everything goes well, when you are too good expert, your policy will get very brittle, very not robust to anything that can go wrong. So adding this recovery demonstration is actually very important for the quality of the demonstration. That's why that dataset is not just about quantity, it's really about quality as well, and this is very difficult to assess. There is no real way, given an offline dataset, to know if it's a good dataset or no, besides training a policy and testing it. So this part is still an ongoing research problem, I think. And again, there is a question of quantity. Of course, the more quantity you have, the more chance you have to cover the variability of the state space. And typically for, let's say, single short horizon task, as a diffusion policy and the one you're going to experience in the tutorials, between 50 and 300 demonstration is enough for a single task. But for a VLA that can do many kind of tasks with a large variability, can be much higher. VLA Pi 0 is 10,000 hours of demonstration. So you can imagine a lot of times, a lot of people spending days and days recording demonstration. And now it can be even more. Last thing I wanted to keep in mind is that at the end of the day, the quality of and the robustness of your policy will all depend on its ability to generalize over new context, over new state space. And we know that it's a neural network policy. At the end of the day, everything will rise on some interpolation over high dimensional space. The magic of a neural network is interpolating in high dimensional space. You need to keep in mind that when you collecting the data, the points are diverse enough such that when you will interpolate over this conditioning, this state space, it will go well. So, do you have any question about machine learning in general? Yeah.
I just want to have an example. What if the task is not like yes or no? Like I'm asking the robot to follow a specific path, like to glue or weld something. And in the same time, I want to acquire a large amount of data from people. But every person will not really follow the essential path. What's your strategy in this case you suggest to follow to not give a
So you mean when you don't want to achieve a specific goals, but you want to follow a specific motions, right?
Yes, exactly. But the input coming from the large amount of data sets coming from different person will have a lot of noise. Like someone will be shaking.
So this is a very interesting research direction. There is, so as I said, the quality of the demonstration depends on expert action. So in this case, if you don't have a good quality action, you will not have a good quality policy. There is a line of research that is about creating good quality policy out of bad demonstration. This is called offline reinforcement learning because it uses ID from offline reinforcement learning. Actually, one of the work I did before is about this. Trying to build a good quality policy out of suboptimal demonstration is a very important research topic. Of course, you need a way to quantify what is good, what is not good. So you need to have a critics. You need to have a way to say, okay, this is what I want, this is not what I want. So it's either through a reward function. So we need to bring back a reward function to say within the dataset which one are good, which one are not good. We need to find a proxy or a different way to explain what you want, what you don't want. But yes, offline reinforcement learning is a line of research that try to explore this research question, and I really believe this is a way to scale this kind of method, because if we can add not just good quality data but any kind of data and just use a part of bits that are good and use them, it's a way to scale them. So yes, it's a very, very interesting research direction. Yep.
So when you want to collect the recovery data, does it matter if you like just say I want to grasp an object and then I start from a random position to create like fake recovery data, or should I deploy the policy and only do the recoveries when it's actually failing?
That's a very good, very, very good question again. There is two ways. The one you mentioned at first, it's possible, of course. It requires the human operators knows what's going to go wrong. And it takes a lot of human experience. So that's why creating a good data set is a kind of art, let's say. You need to know this case is going maybe to fail, and I need to show from these states how it's going to fail and record it. So when you do teleoperation, when you actually doing the recording, it takes a lot of effort, a lot of time, because you need to stop the robot, reset the environment, remove everything to go to the special case you want to demonstrate, start the recording again, do the recovery action, stop and start again. So this reset of environment takes a lot of effort. But you can, when you know what's going to fail, you can do it at the time. A second procedure you mentioned is actually it's called Dagger in the literature. It's actually you train first a model which will have some errors. So you let the policy unfold, and when they enter into a wrong state, you stop it, and then you take over. So you don't have to reset the environment. You let the policy fail, and when it fails, you give it the correct answer afterwards. And you can do that several rounds. You can collect data, train, and deploy again, and do this process again and again and again until the policy improves. It's called Dagger, and it's again old things that has more than 10 years in imitation learning. But yes, it's many companies do this to improve the policy.
Another question: if you want to improve the policy after, can you do some manipulation of the data? For example, if the human is struggling to do the task and it's going a bit slowly, can you just artificially reduce the time between the steps so it looks like it's going faster or stuff like this?
You mean collecting slow demonstration and make them faster afterward?
Fast forward the data.
I've seen some papers that were doing that as well, because most of the time when you do teleoperation, the human is very careful. You know, when you are very focused, you try to do your task and you are not very fast. And that's why the most of the imitation learning policies are not very fast at doing works. There is some works that try to take this slow demonstration and turn them into a fast execution of the task. Some works are trying to do that, yes. But again, you have to identify the part of the trajectory you can go fast without compromising for accuracy, and the part of the task need to be slow and to be very accurate. So this kind of work, usually they try to use some kind of variant or try to metric to find the phases you need to go through, and the phases you can go fast. Yeah.
I have a question about like getting good policies from bad data, like about you said fine reinforcement learning, but I wanted to ask about guided reinforcement learning as well.
About what, sorry?
About guided reinforcement learning.
Guided?
Yeah, guided. Like, let's say that you have a kind of like trajectory recorded, right, from the data, and then, for example, the contact points which are missing from manipulation data. And so you are constructing kind of like a reward function just to fix the contact points in order not to retrain the full reinforcement learning on the whole.
Well, that's very unfortunate because it's a kind of work I did in the past and I didn't include that in this presentation because we weren't going to the lecture. But yes, there are different ways to go from suboptimal demonstration to that, and most of them come from reinforcement learning. So you have at some point you need to train the critics either through reinforcement from a reward function of some way. For example, if you do navigation, you want to go from one state to another, so you can imagine that the best action is the shortest one. And from this data set, you can imagine you have at some point you are at a state, you have a goals, and you have a distribution of action. In your data set, you will have bad action that leads to suboptimal behavior, and good action that you have better and you have good quality. At some point, you want to do some kind of optimization. You want to select in the whole distribution the specific actions that have good performance. And to do that, it's required to do some kind of distribution optimization. In reinforcement learning, classic way is, for example, value iteration, and there is different method to do that. One is called expected regression, that is able to do optimization over a distribution probability given some reward, given some score matrix. There is other method in the landscape that is used. This is called return value conditioning. So you could, for example, when you train your policy with image, robots, and proprioception, you could add additional input, which is, let's say, the reward. You can condition your policy with the score of the action you're going to learn, such that at inference you can force the policy to behave in a good way by using the additional input and have a good scores. And you will force the model to interpolate over something that is good quality. So this is one of the ways to solve these optimization problems. There are downsides about you force the model to be out of distribution sometimes. So again, this is a different presentation, more research work. Yep.
Yeah, I'm still a bit curious why these generative models perform so well in single task imitation learning. Because I think the main argument that the diffusion policy was also making is this multimodality.
Yes.
This multimodality aspect. But there have been some follow-up works that argue that maybe in high-dimensional observation and action spaces and for short horizon control, the multimodality is not so critical. Do you think there's something beyond multimodality and action chunking that makes these models so powerful?
So I've seen this work indeed, and he was arguing that yes, maybe it's not about multimodality, especially on this case when you can fit either go left or right, and actually you can choose going always left or right depending on these frontiers here. Honestly, I think multimodality is still important because that takes the argument that okay, in these cases, for pure control policy, I agree, multimodal maybe is not important. Maybe in some cases you don't really want to be able to do different kind of, maybe in this case, if you always choose the right path, it's okay. Maybe you can do good performing policy even though your output is not very diverse. But this is one way for pure control policy. I think that for research, we want to go beyond that. We want to go beyond purely reactive policy. One of the things I'm studying right now is how to use word model, how to use more inference time compute to improve the performance of these models, to generalize better. And in this specific case, I think that keeping the multimodality of observation is very important. So I would say for the simple things, when you do a classic reactive policy, maybe I agree, multimodality is not that important, or you could be good even though you are not having diverse method. But keeping the multimodality for doing more advanced research, more advanced decision making at inference, I think it's still very important to keep this multimodal behavior, especially when we want to use a word model and other things. So I agree with this paper, but I still think we should keep this generative AI for this problem. Okay, if there is no new question and we have a bit of time, I can quickly go into some technical details, just one about the tutorials, very quickly. So I mentioned about having good quality data, and we mentioned about having flow matching training model, but it's not only this. When you do in practice imitation learning, there is other steps that are very, very important that actually define your whole problems. Typically, you record your data, you end up with a raw data set of episodes. Let's say you have different kind of demonstration, and each of them are observation and action with a different length. Sometimes it's a short one, sometimes it's a long one, so they are varying length. So this is your at the beginning. At the end, you should have a batch of fixed length data to handle with the PyTorch and tensors. In the middle, you have to process your data, and every time I was doing imitation learnings, the part that took most of my time is this handling data. Because we are doing learning-based, we are doing data-driven methods. Everything is about how you process your data. And there is a number of steps that are actually very important and actually define what you're doing. One of them is data normalization. So of course, you know that neural networks behave better if all your data are somehow between -1 and n1 because of the activation function. So it's always a good idea to transform your data between -1 and 1. So keep in mind that it's a step you shouldn't forget. Also, from your raw data, you need to change sometimes representation of your data, doing some kind of encoding. The most classic way to do that is you have rotation, and rotation are complicated. You could be axis angle, quaternion, rotation matrix. The representation that works well with learning is usually a 6D format, which end up with the 2 first column of rotation matrix. It's a classic paper about that, but again, changing your representation of data is an important steps. Another example is how you represent your action. So you can think about the frame in which they are expressed, could be absolute frame or the word frame. If you are doing with local manipulation or a humanoid that moves, the frame in which it is expressed is important. Also, you could think about a relative action sometimes. Instead of learning action, you can learn delta action all the time, so actions that are relative to the beginning of the sequence. Again, there are many design choices to be made at these steps. There are some papers say that every paper tries to say, okay, my method is different, I did some comparison, etc. But there is no representation for action that is best in all cases. So sometimes you need to try all of them and see the one what works the best for your problem. There is always a step of data augmentation. Typically, you want to include some kind of invariance prior in your data. Most classical example is the images. You have your images, you want to randomize the lightness, the contrast, the bit of the color, so that your policy gets a bit more robust to distractors and to change of light in your input. So this is true for image generation. For action, maybe you could include some kind of invariance, some kind of translation, rotation in your problems. Again, this is task specific. And the most important part is how you create your batches for training. Typically, you start with a demonstration of different lengths, and you need to create a fixed length training batch for your data. And this is most of your problem, most of your work is to define this step, because this define what you're actually learning. And for every task, this step is essential. So I will just go quickly one example that we're going to go in the tutorials, but there are many other ways to do that. Typically, you want to learn a policy that go from observation, maybe one goal, which is the goal observation you want to reach, and the sequence of action. And one assumption you could do is how you select this goal here. Because in the original data, you just have a long list of observation and action. And how you select the goal you want to extract to build a goal condition policy is one of the design choices that are very important. There are many options, of course. One of the simplest assumptions you can do is, okay, in the demonstration I have, the last observation in the data is always the goal. So this is the easiest things we can do, and this is what we have applied in the tutorials today. typically the procedure is the following. You have your raw demonstration. You're going to sample an observation in the whole data set. That is start at least each time step before the end of the episode, because you want to extract observation and the following edge, let's say horizon action, and then you're going to extract the goal in as observation at the end of the selected episode. So this is not technically it's not very difficult to implement this. You need to do some PyTorch tensor manipulation to do that efficiently in batch, but the choice you're making here at how you're going to select randomly this observation or how you're going to select your goal really define your problem, define the whole policy you're learning. It is the most important part you need to design when you train intention learning policy. So if I don't know if we have a lot of time left, maybe no, but I wanted. Okay. The last slide was about model architecture. You can use MLP, you can use film, you can use unit model, you can use transformers. If you have choices, use transformers, but it takes time. So in the lecture, we're going to use a classic old-time MLP. Yeah, simple. Okay. Thank you very much.